I'm on the following page here. I accidentally wrote on it. Sorry while I was taking notes. But this is actually the delayed neutron generation time versus lifetime. So it too starts at the fission event. Then there's the amount of time. Well, you remember we stopped about 10 to the minus 14th. Here's the big difference. The release time is greater than 10 to the minus 14th seconds for a delayed neutron, and on average, it is 12.7 seconds. It shows up a magnitude later than the prompt neutrons do. Then it goes through the same thing. It slows down, so it has a slowing down length and a slowing down time. And guess what? Its slowing down time is 10 to the minus 6 seconds. Because once they're here and they're released, there's only a slight energy difference, remember, 2 mega electron volts versus 0.5. So one extra collision doesn't take but a fraction of a second. So now here, once it's slowing down and it's become thermal, it's thermal right there, it will continue on. The neutron will get absorbed right here. This was the thermal diffusion length, and the time associated with it is the same exact time, 10 to the minus 4th seconds. And this one here was 12.7. Once again, a generation time is the time from the fission event to reabsorption. This is a generation, and the generation time for a delayed neutron then, instead of being, like we said, for a prompt neutron, which was L star, which was prompt, its prompt neutron generation time was 10 to the minus 4th seconds. Let's look at a delayed neutron. We'll call this LD, delayed neutron generation time. This is for a delayed. What is that total time going to be? 12.7 seconds. That's seconds. Plus 10 to the minus 6. 12.7 plus 10 to the minus 6 plus 10 to the minus 4th seconds. So essentially, LD, the delayed neutron generation time, is 12.7 seconds versus 10 to the minus 4th seconds for a prompt neutron. So it is vitally important that our delayed neutrons, even though they represent a small fraction of the core, they are slowing the entire process down by magnitudes and magnitudes. So it is vitally important that we always have them in control. That even though they're a small fraction, that small fraction is keeping this a controllable reactor. Keep that in mind. Before we go, there's a knowledge requirement there. Define the neutron lifetime, and the neutron generation time was on the previous page, if you'll recall. Right here, right there. So know the difference between a generation time and a lifetime. There's not much difference in the lifetime of once it's released, there's not much difference between a lifetime of a prompt and delayed, but their generation time is massively different due to their massively different release time.